Thank you, Martin. This is my first in-person international meeting. I'm enjoying face-to-face communication. Thank you for this. And my talk is on the triangular relations of electrons, or entangled relations of electrons. One is the on top is a spin liquid, and the other one is the charge gas. And first, I'm going to talk about the business status of the quantum spin research, particularly on the magnetic acids. And second, I show you the different experiment results and the both spin liquid candidate. Then I switch to the topics of the charge glass, where I'd like to emphasize that the quantum manifestations of the electron glass charge glass. Okay, they are my very strong collaborators, and today's talk is based on collaboration with these colleagues, many colleagues in my university, so the outside of our university. Okay, and yesterday, Michelle gave a very excellent and detailed introductory talk about the what is molecular materials. So I have no need to repeat that. But here I'd like to emphasize that the one advantageous point of the organic materials, in inorganic materials, for example, the metallic copper forms a face-centered cubic lattice, but we cannot change the crystal structures. However, in molecular materials, even in the same molecular compositions, they have many polycrystals, not polymorphism, many kind of the molecular arrangements, even for the same molecular arrangement. This is the example of the arrangement of molecules, which is specified by the Greek character alpha, beta, theta, many molecular arrangements of the same molecules, PDTTF. So we enjoy the diverse physics and the same compositions based on the single molecular species ET. For example, in this molecular materials, you enjoyed the Dirac physics. And today I'd like to talk about the two topics. One is the mode physics, particularly in the spin liquid physics. This physics is going on, this molecular arrangement, the half-field band triangular lattice. And charge glass physics emerges in this class of materials, which this molecular arrangement is specified by the theta type. Okay, so here I'd like to talk about this spin liquid physics and then the charge glass physics or charge liquid physics. Okay, first, this is a very famous and well-known cartoon, which depicted the RBB, resonating valence bond state, invented by, proposed by Phil Anderson. And the essential feature of the RBB is it's exactly the same as the benzene. The benzene has two degenerate states, and two degenerate states are quantum mechanically resonating. And on triangular lattice, the similar thing happens, but in this case, the degenerate bonding arrangements are infinite. An infinite number of the configurations are available. But these are added in quantum mechanically. In that case, the RBB is realized. However, these states are or, in that case, is a valence bond glass. So arbitrarily, one state are selected at low temperatures. But if the one particular bonding arrangement with a very regular arrangement is realized and it has a very stable state, the valence bond crystal, the valence bond solid are realized. Okay. This is the concept of the LBB. But based on the LBB, even in this common concept, we have a variety of the spin liquid states, but I cannot follow all of the theoretical proposal. But this is the representative one. This is the gapped LBB. This is original LBB proposed by the Anderson, or the gapless LBB with the spin-on surface, or another kind of the gapless LBB is available, but in this case the gap is nodal, so Dirac point, and the chiral spin liquid is also proposed. But so the ground state and excitation, magnetic excitation from the ground state is one clue to exploring the nature of the quantum spin liquid. So okay, these are two representative systems, organic systems of the quantum spin liquid candidate. One is the couple ET2 CO2CN3, and the other one is the Kato-san's material, the MIT. Both materials has a quasi-triangular lattice, so I don't repeat that the essential features of these materials because Michel gave explanation yesterday. So okay, this is the very early data, and also Michel showed yesterday. This is a comparison of the NMR spectra between the two materials, the isotropic triangular lattice and the anisotropic triangular lattice. No change of the NMR line. We give tells us that the no magnetic order. This is a consensus among in this community. So no magnetic order. At least in the low magnetic field, that is a consensus. However, as you know yesterday, the gap is finite or not is very chaotic, still chaotic now. And specific heat suggested the finite gap. Finite gamma and gapless, and the thermal conductivity tells us that the very small gap. And Municipal experiments suggested another kind of gap, and this is the phase diagram. This is a cartoon, but this cartoon was drawn based on the experimental data performed by Pratt et al. And in the low magnetic field, it's a temperature magnetic field. In the low magnetic field regions, there is no internal magnetic field. But this is a critical point, he said. Above this magnetic field, there is an inhomogeneous magnetic field that emerges and induced by magnetic field. If this point is a critical point from the gap state, and then, for example, the BEC of the bosonic spinors, in that case, at ambient pressure, this system should have a spin gap of 4 millikelvin, very, very small. So 4 millikelvin, 400 millikelvin, and gapless gamma, finite gamma. So completely reversed in this problem. Okay, very recent experiments data emerged from the Martin Dresser's group. It's a new ESR temperature and the ESR intensity. So it's a ESR susceptibility. This suggests that indicates that the paramagnetic spin susceptibility decreases, say below 10 kelvins. And this is the NMR, carbon-30 NMR data in my group. The data is consistent with the ESL experiments. Below 10 kelvins, the NML spin shift. It's a night shift in the metric state, but in this case, insulated. So spin shift goes down. So paramagnetic susceptibilities goes down below 10 Kelvin, and that is reproduced in the NML experiments. One additional information in NML is line broadening occurs below 6 Kelvin. This means that the inhomogeneous local field is generated, induced by magnetic field. This is consistent with the USL experiments. In the USL experiments, in this colored, pink colored or purple colored regions, there is the inhomogeneous magnetic field that is induced by magnetic external field. Okay, but the curious is the NML relaxation rate, and this is symbol is becomes a ghost, right? Sorry. The different magnetic field and different magnetic orientations, these gave nearly the same data, NML relaxation. In the carbon-30 NML relaxation rate, 1 over T1 is decreasing. Okay, it's consistent with the shift and then ESL. But proton NML relaxation rate shows a very sharp peak below 6 Kelvin. So some anomaly occurs in proton NML. But why carbon-30 T1 inverse and the proton T1 inverse is different is we have a similar scenario, but later I'd like to discuss about that. Okay. Okay. As for, regarding this curious behavior of the proton NML relaxation, this is expanded figures. Okay. Say. Okay, low magnetic field, at low magnetic field, 0.34 Tesla, the relaxation rate shows a peak here. And then at higher magnetic fields, the peak is, peak position is shifted to higher temperatures. And then, yeah. But this peak formation is sometimes encountered in the impurities. So we cannot rule out the effect of impurities. But this feature is not consistent with impurities. But an impurity contribution is worked in this case. Usually when you increase magnetic field, the Zeeman gap is increasing. So the NML relaxation rate is suppressed in the whole temperature range. But however, you see in this temperature range, a higher magnetic field and the relaxation rate goes higher. So this feature appears inconsistent with the impurity effect. And another feature of this relaxation rate, the peak formation of relaxation rate, is the reproducibility. This view graph shows the data taken for separate samples. So the two samples show nearly the same behavior. Proton is, in the edge of the molecule. Edge of the molecule. Yeah. And here, this is not drawn. The proton is here, and here, at the edge. So hyperfine coupling is very small.
Very far from the top. The copper is up far.
Yeah.
Where's the copper?
Copper is a non-magnetic here. The copper 2CN3.
This is in the ET. This is in the ET layer.
This is the ET layer.
So the proton is in that.
Yeah, it's edge of the
So
yeah.
it's a basin.
Yes. Proton is here, and the copper is like here, and in the insulating way.
Can you put
in the ET molecules?
yes?
Yeah, sulfur, nitrogen. It's difficult because of no nitrogen. carbon-13 is a, yeah. Later, yeah, okay. This is carbon-13. This is carbon-13 NMR. It's a proton NMR. And the sulfur is also available, but it's very, very expensive. Sulfur isotope. We need sulfur isotope to do NMR experiment.
So you get different, so if I put these things next to each other, it's clearly the problem there. In the layers versus
In the edge layer. Yeah, different. So we have a similar story. One is the carbon is located on the center of the molecule, so very, very large hyperfine magnetic field. So if there is some, yeah. Yeah.
You're the poppers, the other is something else.
No. Because hyperfine coupling is different, but the proton is also detect the electron dynamics, because no other relaxation mechanism at low temperatures. At high temperatures, H-ray motion gives some motional contribution to the NMR relaxation rate, but at high temperatures. Yeah.
So one of them shows us
6 element here.
Yeah, which the other one does not.
Yeah.
So that sort of implicates the T molecule in the 6-degree anomaly, but not the layers of
one clue is the this one. By Mueller experiments, they detected the very generation of the inhomogeneous field here. Yeah, there is a moment in homogeneous.
Why I see something at 6 degrees for the hydrogen, but not for the
So the point is when the magnetic moment is generated, at carbon site, the carbon has a very large hyperfine coupling constant. So carbon site cannot detect the on-site some large moment. So carbon NMR sees that the other hosting site, the proton NMR covers detects the whole body.
Yeah, that's the point.
So I think that yeah. So I think that the low temperature peak formation is a separate problem from the 6 Kelvin. Okay, both NMR relaxation rate goes to is susceptibility decreasing at 6 Kelvin, but below 6 Kelvin something happens. This something happens. Something anomalous phase. Anomalous phase can be detected by differently at proton NMR and carbon site. Yeah. You are saying? Yeah. This one? Yeah. A little bit, yes.
This top block here, this is this peak here.
Yeah. Low temperatures. 6 Kelvin here. Not peak, minimum. Minimum is corresponds to 6 Kelvin. Yeah.
Of course, the meaning of these, but I prefer these relaxation rates is 500 fine. Because the coupling is so much stronger for the 13, of course, we'd expect that to be multiplied out. I mean, if I try to model this in terms of some generalized independence acceptability, I feel differently.
But if you convert this one over T1 is converted to the chi double prime is maybe T1T.
Yeah.
1 over T1T should be yeah. In that case, T1T is always go like this, go up.
But they are different. What's
They're small.
They're different projections.
Yeah.
Different averages over Q space of the tidal prime. There's
Between the two nuclei, you see.
Yeah.
Yeah.
in the same way.
But in this case, the situation is completely different from couple because the molecular orbital is sitting on the BET molecules, and then the exchange interactions between the
So your second pi double prime. So you have your spin liquid with the pi double prime.
Mhm.
Your omega and then the 2 is pi double prime over as part of field omega over divided by omega.
Mhm.
The omega goes to the limit and then multiplied by some weighting factor which has to do with the position of the atom. So it's a bunch of processes.
Yeah.
So I'm just trying to understand which part of the spin liquid response I'm most sensitive to is if Q is 0, if it's pi, or where really, how can I relate this to the spin liquid stuff?
But I want to say that in this materials, the form factor, Q dependence of form is nearly no Q dependent. No Q dependent. Because okay, please take a please consider one molecule here, So in the copper oxide, okay, if you see the copper nucleus here, and then in the neighboring side, the copper spins, for example, in these directions. This copper side shows a very internal field. It's an indirect field. But in this case, molecule and molecule is overlapping is very small. So if the one spins or spin 1/2 is sitting in the neighboring molecules, this local field is very, very small. So in the molecular materials, carbon-13 has a nearly negligible Q dependence. Hydrogen is a very subtle problem because okay, and the hydrogen it's a very subtle situations because the hydrogen here. So the hyperfine coupling constant is very small. However, the dipole coupling is becomes more significant than carbon side. So the form factor of Q is very different.
I mean, it must be different because you're getting a different temperature.
Sorry. Okay.
Rephrase the question. If both measurements are detecting the same magnetic susceptibility, and if there is a momentum independent of the form factor, the naive probe would expect that these two probes should be right on top of each other. They are obviously not right. So the question is, what mechanism makes them look different?
Yeah. One explanation is okay. Okay, you see, a low temperatures, NMR language is going up. So at low temperatures, maybe NMR spectral wiped out because local, yeah. So yeah. So carbon-13 relaxation rate proves that the relaxation due to the spin diffusions. In the very active, spin active regions, we cannot align that the nucleus spins on the very active electron spin side because the spectral line is out of our NMR range. So this detects that
So the relaxation rate becomes comparable to the actual frequency.
Yeah.
Which over there you can see.
Yeah. So this is spin diffusion limited relaxation rate. But this proto-NMR detects all of the average of the all relaxation rate. Yeah.
Then negative is to go to 0.
Yeah. No 0. Yes, that's a point. Okay, ESL detected the paramagnetic spin stability that should go to 0. except for the impurity spins. But NMR detects a whole internal field. Paramagnetic component is decreasing, but something remains. I think that below 6 Kelvin, some magnetic organization appears. I think that is what my speculation. You're saying that maybe this one is finite. Yeah. So in experiments, this is a chemical shift. Okay, I'm sorry. This is a chemical shift. Chemical shift is a finite, but we subtracted the chemical shift. So this is a origin of the spin shift. Okay, so there is a finite internal magnetic field in carbon-30 NMR. So the paramagnetic spin is already decreasing, but some finite internal magnetic field is remains, I think. But this is not paramagnetic, I think. Some magnetic organization is related to the maybe this internal magnetic field, I think. I don't know. For example, in superconducting state, in the superconducting state is in the S-wave superconductivity is a gap closed, but under the magnetic field, for example, FFL state is a Andreev band state. The quasi-particles appears. So if you do the same experiments in the FFL states in NMR, maybe it's a S-wave, the gap superconductivity. However, under the magnetic field, maybe a finite quasi-particle spin shift should be observed. So I think that it's controversial, not it's consistent or not consistent with the gap state. It's a very not straightforward. But I think that in the zero magnetic field, if the system is gapped, but even in this state under the magnetic field, we may have some finite gap. There's one. Inhomogeneous. Inhomogeneous state.
There are many different sites.
Yeah.
Okay, so you have some freezing.
Freezing, or I guess that there's some FFL-like state of the spin of the Milky Way. It's a depend on
magnetic field.
yes, magnetic field. It's a proportional to the magnetic field. It's not frozen state. In the frozen state, for example, spin glass state, in that case, the local field is not so sensitive to the magnetic field because, like the magnetic ordered state, it's like a paramagnetic because the line width is proportional to the magnetic field. So magnetic linearly, roughly linearly. Okay. By the way.
No, just the one.
Okay. Okay, so the spin gap state, the paramagnetic spin goes down. So okay, if we call this behavior spin gap state, the spin gap state is maybe unconventional because we have several strange features. One is the okay, this one. Okay, this anomalous peak formation. The other one is if we applied magnetic field 16 Tesla, but this decrease of night shift is very robust and not changed. In conventional, for example, the singlet states or balanced bond solid state, in that case, maybe the 10 Kelvin is a characteristic temperature of the gap. Maybe under 16 kelvins, maybe this gap is closed or shifted or decreases, but very robust. And in NQR experiments, the NQR lines, the position and width doesn't so much change. So as far as I know, there is no indication of the similar breaking below 6 Kelvin. So I don't know but the origin of the spin gap state, but the valence bond or similar breaking state is unlikely. That is my guess. Okay, and this is the pressure dependence of anomaly relaxation rate, a proton anomaly relaxation rate. And this is spin liquid at 3 kilobar and ambient pressure. And if you apply 4 kilobar to this material, this system undergoes a mode transition to the metallic state. In the metallic state, this peak is completely gone. So this peak formation is very intrinsic, not intrinsic, specific to quantum spin liquid state. Okay, 6 Kelvin anomaly. This is maybe you well know this anomaly. Michelle explained. So 6 Kelvin is a very key temperatures. So we searched for quantum oscillations in this spin liquid candidate because the spin on Fermi surface, the model of spin on Fermi surface is a one candidate of the quantum spin liquid. So with collaboration with the ISSP guys in University of Tokyo, we did the high field experiments in torque and magnetocaloric effect and direct constant and ultrasonic velocities. But you see, unfortunately, we did not see any indication of quantum oscillations. And this is the torque versus t squared. So this slope gives you the spin susceptibilities. Spin susceptibilities is constant up to 40 Tesla, no oscillations. And yeah, you can see no oscillations in this. But we have several interesting features. For example, ultrasonic velocity. You see the anomaly kink from low temperature region to the high temperature regions. And this kink, this anomaly may be related to the 6 Kelvin anomaly. So this is a field dependence of the 6 Kelvin anomaly. So if you plot this anomaly as a function of a magnetic field, the behavior looks like this. So very, very robust. The 6 Kelvin at 0 magnetic field decreases to 4 point something at 50 Tesla. So this is very consistent with our high field anomaly experience. Even at 15 Tesla, the spin gap-like behavior is very robust against magnetic field. So I think that this high field behavior suggests that this decrease of the paramagnetic spin susceptibility is a very unconventional phenomenon, I think. But anyway, as April, you asked yesterday, is there any evidence for the mobile spinors? But at present, as far as I know, we have no clear indications of the mobile spinors, except for the specific heat gamma, but which can be interpreted as this glass-like or tunneling-like. So in this sense, we have at present, no clear evidence for the mobile spinors. Okay. Next, can I switch to this? I have a time.
Let's go on.
Okay.
Yeah. Okay. Let's get 1 hour class.
Okay. Now, okay. Okay. And we have very interesting materials. Is doped triangular lattice, and that is this materials copper arrangement. Okay, the same copper arrangement. Copper 84 mercury bromide. This material is synthesized by Russian group, Lyubovskaya. this material is very, very interesting. If the content of the mercury is 3, in that case, the one hole sitting on the one diamond, so the multi insulated. However, this missing portion of 0.11 gives the whole doping. It's 11% whole doping. But this non-stoichiometry occurs due to the incommensurate lattice of the mercury against the ET lattice. So we cannot vary this content, unfortunately. But this is the random. This is not a random defect. It's that this mercury forms an incommensurate lattice against the ET lattice. So the disorder is minimized in this system compared with the conventional doped systems. But anyway, we have 11% whole doped triangular lattice materials. Okay, let's compare the conductivity and magnetism of the two materials. And blue symbol shows the non-doped quantum spin liquid candidate, and this red symbol shows these doped materials. Resistivity is completely different. Non-doped system is not insulated, but the doped system is metallic, and then undergoes a superconducting transition below maybe 2 or 4 kelvins. So this is doping effect. So, however, the interesting point is the magnetic properties. And if the spin susceptibility and temperature is normalized to the energy of J, the two materials show nearly exactly the same behavior in static spin susceptibility and also in the dynamic spin susceptibilities. At low temperatures, this is a low temperature phase below 6 kelvins. This anomalous phase in non-doped spin liquid phase is replaced by the superconductivity in this doped system. The superconductivity I show later. Okay, this is the comparison of the phase diagrams of two materials. This is non-doped cases, pressure and temperature. Okay. And the spin liquid phase and the 6 Kelvin anomaly phase, and superconductivity occurs. Yeah, this is critical pressure. And in 11% whole doped system here, this spin liquid mode insulator is replaced by the non-film liquid phase, as I show you later. And yeah.
So on which basis do you say that the superconductivity DC light, for example?
Yeah, later I'd like to show. Yeah.
Yeah.
Okay, and this is the pressure dependence of the whole coefficient, which is roughly inverse of the Carrier numbers. Like at the low pressure range below 0.5 GPa, the whole coefficient is large, but this whole coefficient is rapidly decreases at above 0.5 kelvins as a coefficient is leveling off. This means that in this low pressure range is a very the density of the holes is very small. Maybe the doped hole, only the doped holes are mobile, but at high pressure range, is a double occupancies are allowed, and then the holons and doublons are many holons and doublons are moving around. So the whole film surface contribute to the conductivity. So this is a small low carrier density material crosses over to the high carrier density metal with strongly correlated nature. And interestingly, TC forms a dome, and then the top of the dome is located in this crossover region. Okay, this is the exponent, temperature exponent of the normal state resistivity. Let's take a look at this figure, the temperature and pressures and the exponent. The yellow color means the exponent is unity, so non-film liquid. And this non-film liquid is sharply changed to the film liquid region. So, so this is non-film liquid region here. changes to the film liquid region here. And this crossover is very, very sharp. And this is the Zeebeck effect, Zeebeck coefficient. And Zeebeck coefficient divided by temperature is plotted as a function of temperature in the logarithmic scales. And the low temperature, low pressure regions, yeah. In case you see the S over T goes up nearly the logarithmic manner. But at high pressure regions, the one with S over T is nearly constant. This is a conventional behavior of conventional metals. Okay, so in this non-film liquid regions, the logarithmic dependence of S over T, which suggests the quantum criticality, which is widely discussed in the diverse materials. Okay, the interesting point is that this red region is a quantum critical region here. So this is extended in a finite parameter range. So this is quantum critical phase, not a quantum critical point. Okay, and such a quantum critical phase is reported in several materials, and one is the heavy electron systems, cerium, palladium, aluminum. The people discussed that this spin liquid features of the metallic state stabilizes the quantum critical phase in the quantum breakdown scenario. The point is the frustration makes the quantum critical point extends the quantum critical phase. In our case, the background phase is a quantum spin liquid. If so, the quantum critical phase is likely to stay in a finite parameter range, I think. Okay. This coefficient of the logarithmic term is an indication of the strength of the quantum criticality. Okay, this is okay. In this material is the gamma prime value is roughly unity. Okay, and this value is larger than the copper oxide and the ion nuclide materials, and one order of magnitude larger or several times larger. And these values is smaller than the heavy electron materials. The gamma prime values is very, very high in heavy electron systems. This quantum criticality is in between the heavy electron systems, and then this is a cuprate and then iron superconductors. Okay, I switch to the BC crossover. Okay, we measured the upper critical field. To do that, the students measured the resistivity as a function of temperature and pressure. And this is the color shows the value of resistivity. The red color means that the normal state resistivity. So blue colors is vanishing, nearly zero values. Okay, you see at a low pressure range, it's a zero temperature range here, but this is the color gradually changes. The region of the color changes larger in low pressure region. This means that the vortex liquid region is extended in the low pressure range. But at high pressure range, it's a upper critical field is very, very small. Okay. So from these figures, we determine the upper critical field, and then coherence length is determined. And this is the pressure dependence of the coherence length. Low pressure regions, coherence length is very small. Okay, at the high pressures, it's a large, maybe of the order of 200 angstrom. Okay, we know the carrier numbers from Hall coefficient measurements. So from a whole number, we estimate the Fermi velocity Kf. So this is view graph shows the Kfc versus the pressure. At low pressure ranges, the Kfc is 3 or 2. This means that the overlapping of the Cooper pairs is a pair. It's very. However, at high pressures, the Kfc is 50 or 60. Okay, it's a many Cooper pairs overlapping as expected in the conventional BCS. So from these results, we can we think that this is a pressure-induced BC to BCS crossover. But later, I'd like to raise some question about this the BCS crossover from our recent results. Okay, superfluid density. Sorry, you heard that. Okay. We measured the Nernst effect at different pressures, low pressures, middle pressures, high pressures. Low pressure range is the Nernst effect is very high, up to 9 Tesla. So superconductivity persist even up to over 9 Tesla. So very strong. The superconductivity very robust against magnetic field. And this anomalous superconductivity BC regimes. But however, at high pressures, as expected, the Nernst effect easily suppressed. Okay. And this is this color plot shows the magnitude of Nernst signals at 9 Tesla in the plane of temperature and pressure. This is a zero magnetic field TC here. Okay, you see this is a normal state. So you see the finite Nernst signal in this region. This means that in these regions, far above TC, you have the preformed Cooper pairs. And this is likely under the occupancy. Okay, superfluid density. We follow the measurements, the method of the Michelin you did 30 years ago. Yeah, very beautiful experience. So I followed this method, and then that is the from magnetization measurements. You get the penetration depths. Okay, through these equations. Then once you know the penetration depths, you know the superfluid density. Well, according to these relations. Okay, the results here. And this is a U over T, and this is the doping. This plane is a half-field planes, and U over T here. So NCS and bromine. The bromine and NCS, the M. Okay, please take a look at the superfluid density here. Okay, and this material, the doped spin liquid candidate, has a very low superfluid densities compared with the half-field materials. So I think that the maybe 50% or 20% of total carriers contribute. Only this fraction contribute to the superconductivity. So other portion maybe remain incoherent. Okay. And another interesting point is the ratio of TC and the Fermi temperature. Fermi temperature is a nominal Fermi temperature estimated from this penetration depth is at 0.1. It's very high. It's orders of magnitude larger than the BCS framework. And this Mercury compound, this present system is located here, like this. Okay, so everything looks like underdoped cuprates. However, I'd like to emphasize that in these systems, there is no competing or coexisting phases like charge order, charge density wave, or other spin density wave. So maybe the overall features very resemble the behaviors of underdoped cuprates, that this system has no competing or no coexisting orders, which complicates the physics of underdoped cuprates. So this is a very unique point. Okay.
One question.
Yes.
So you have the mechanic version of it.
Yeah.
So how do you know what is on the insulating side? Because you cannot apply negative pressure. So I mean, then you don't know what is the magnetic ground state.
I don't know, but we cannot apply negative pressures.
Yeah, sure, but I mean, then the statement that there is nothing nearby to the space space is just not available.
I
I
cannot
mean,
say.
you have only the mechanic compound, but
Yeah. Ah, okay. I can say, okay, I can say something about it. Okay. We have this. Okay, skip this. Okay, we did recently the pressure experiments where we combined the hydrostatic and uniaxial pressure. Okay, and these materials, and this is very sophisticated method. And by very simple assumptions, we calculated the transfer integral and the boundary structures rough estimate. And then U over W and the T prime over T. Roughly speaking, hydrostatic pressures varies U over W like this. And uniaxial pressure changes the frustration and also U over W this, and in the directions. So please take a look at this axis. U over W is constant, but the T prime over T is changed. This is a triangular lattice. It's a toward scalar lattice. It is a toward weakly coupled one-dimensional change. Okay. So this color shows that the resistivity values are 10 kelvins. Okay, that means that very high resistivity here. Yeah, and this is metallic. So this means that if you control fluctuations, if you release the fluctuations, namely when the system goes toward the scalars, the resistivity goes up. But there's a transfer. But I think that maybe charge order or some spin orders, it's a salient, such an order is going to appear. But this is a resistivity data. And in these regions, resistivity is increasing, is insulating. But you see the increasing feature is a very occurs even at room temperatures, very high temperatures. So I think that it's like a mod insulator, I think. Yeah. Yeah. Unfortunately, no. Unfortunately, no. The doping level is determined by chemistry between ET, bromine, and mercury. So every time Lyubovskaya synthesized these materials, always 2.89. I heard. So anyway, so as for your questions, maybe if we change the frustrations, so maybe we may we can go to the insulating side, but the nature of the insulating state is still unclear. Okay, it's the nature of the superconductivity. Okay, this is the low temperature behavior of the NMR night shift and NMR 1 over T1 T. Okay, this is the conventional behavior of the half field band 10 Kelvin superconductors, non-doped. And this behavior is very typical. Night shift is constant down to TC, and below TC, the night shift is suddenly decreases. And 1 over T1 T is also constant down to TC, the below TC, of course. But it non-doped. You say that the experimental results of the carrier density. But anyway, people believe that the one carrier per diamond, one carrier per diamond, one pole per diamond. Yeah. Some people measure the whole coefficient, Murata sense coefficient. Maybe the value is nearly the expected values. I think. Not exactly, but because in the whole coefficient measurements, in for organic materials, it's not so easy because because even single crystal contains a mosaic of some boundaries. So electric current usually, yeah. It's no. And I mean that at higher temperatures, at high, you saying that it's a compensated metal, you see, so it's a zero. But I see. Okay. Okay. Anyway, for these materials, the night shift starts to decrease at much higher temperatures. For example, 20 Kelvin, 30 Kelvin, and then this decrease is accelerated at lower temperatures. Okay, this is 8 Kelvin. Sorry, this is the behavior of the under the 8 Tesla perpendicular to the magnetic conducting layers, even at high magnetic fields. Spin sensibility, night shift keep decreasing. But if you apply magnetic field, lower magnetic field parallel to the conducting layer, the night shift is further decreasing. So this suggests that the superconductivity is a singlet, I think. And this is the T1, 1 over T1T is a TC here, but TC is about 4 Kelvin, 4 or 5 Kelvins. But 1 over T1T decreases, starts to decrease around 8 kelvins, roughly twice of TC. Yeah. So one scenario of this for explaining this behavior is preformed pair starts to be generated at roughly twice of TC, maybe 8 Kelvin here. This is the signature of the onset of the preformed pairs. However, night shift starts to decrease at much higher temperature. So means that I think that this material has a Sill gap, very small Sill gap, which may open in a part of the film surface, like under doped plates, but no competing orders. It still remains incoherent, I think. And the preformed pairs occurs below 8 Kelvin, roughly twice the TC here. And then the decrease of the night shift is accelerated. So that's one plausible scenario to explain these materials. Okay, the nature of the superconductivity, again, additional feature is the temperature dependence of the 1 over T1. This is T cube, but lowest temperature is insufficient. So we should do the experiments at much lower temperature. But at present, the behavior appears nodal superconductivity. Okay, so singlet nodal, so the superconductivity. But if we apply perpendicular, the same field, we did not do such experiments. Maybe I guess that if you apply the perpendicular field of the same magnitude, maybe roughly this. Because if you we did the measurements under 8 Tesla, 4 Tesla, the perpendicular to the conducting layers. 4 Tesla data is like this.
So what's the other
Critical field, we cannot say critical field because okay, it is difficult to determine the critical field. And resistivity is okay, like this. But yeah, however, but you see in the nurse effect does not decrease, maybe much higher. So I don't know. Kuiper pairs are still alive, higher magnetic field, I think. Okay. So from these results, one question is raised. The BC regime, the BC regime, this results suggest that the superconductivity is nodal singlet, probably deviated superconductivity. However, if the BCS crossover occurs in the BCS limit, BEC regime, the coupling is strong. So theoretically, maybe BEC, the superconductivity in the BEC regime should be fully gapped, I think. So I don't know how to explain this discrepancies between the NMR features of the nodal superconductivity and BEC-like other features. Okay, this is a puzzling, I think.
What do you see like 4K in the upper
Maybe much higher, I think.
Oh, so it violates how you do.
Yes, completely violated. Yeah, completely violated, yes. And in transport measurements performed by NIST, Uji-san, maybe he measured the resistivity at high temperatures. So maybe resistivity zero persists up to 15 Tesla. At much higher lower temperatures, yeah. So I think that these are resistivity measurements. So I think that the near field like upper critical is much higher, I think. So it's very strange. Maybe 3 or 4 times higher than the larger than the Pauli limiting field, I think. Yeah, but yeah, gap in nature large, but in conventional BEC scenario, the couplings should be strong. So all of the BC pairing should be S-wave-like. That is a theoretical prediction. So I don't know.
Is it flat?
Yeah, it's roughly scale to the spin of no, like this, decreasing. Yeah. Roughly scale to the spin susceptibility. Roughly. Yes. This room temperature. J is in this case for this material is 160 Kelvin. Yeah. And this non-doped case 250 Kelvin, more large. This J is consistent with the rough estimate of the U over T square over U. The other okay. Anyway, we should stop here. Okay. Next time if possible, next time I'll go to the electron glass. Oh, just flash. No, anyway. Okay. I'm sorry. Time up.
Okay.